There is a thing which is called Ayurveda, Joytika is not here, she could have corrected me, which is the science of life. So why do I go into this? Well, first of all, it's a 5,000-year theory before John Walsh, because he showed us today that medicine is useless. But it's a system of natural healing, and its origin is in Vedic culture of India. And the meaning of this is the science of life, is the air of life, and Veda is sounds or knowledge. We know that Tibetan medicine, traditional Chinese medicine, early Greek medicine, all roots in Ayurveda. It helps people to stay vital while realizing their full human potential. And it provides guidelines on ideal daily and seasonal routines, diet, behavior, proper use of senses, everything. Health is a balanced and dynamic integration between environment, body, mind, and spirit. This is what this theory teaches us about. So now, it has 5 elements: air, water, fire, earth, and ether or space. And there is some connection between these elements, and they provide 3 main forces. So, well, first of all, there are 3 fundamental energies: movement, transformation, and structure, and then the forces. So you have Vata, which is wind, which is connection between ether and air, or space and air. Pitta is a fire, and Kapha is earth, and we can see that fire is a connection between, Pitta is connection between fire and water, and Kapha is connection between earth and water. So Don was asking me when fire is coming in. Here's what is coming in. Now, every person has a unique proportion of these 3 forces, and they form person's nature. But they can be changed from one to another. So if one has a preference of Vata, which is, then the person will be thin, light, enthusiastic, energetic, and changeable. It sounds like a freshman. Pitta is intense, intelligent, goal-oriented, and have a strong appetite for life and finishing the dissertation. So it's like somebody who is finishing. And Kapha is easygoing, methodical, and nurturing. It sounds like a thesis advisor. The goals of Ayurveda is intensify a person's ideal state of balance, determine where they are out of balance, improve the balance, offer interventions using diet, herbs, aromatherapy, massage, treatment, music, and meditation, which restores the balance. And of course, it also only works if you don't have a red tide. Now, if we look on the elements of Ayurveda, we have an idea. Why don't we call it a branch of geophysical fluid dynamics? But in this case, we have 2 new primary forces which are not accounted for. First is air and earth. And this is the realm of Esamati, and in our language we call it meteorology. And the other one is water plus space, and this is where Jesse is working, and this is combination of physical oceanography and planetary science. Okay, so this is easy introduction. Now it will become a little more complicated. So the first is we deal with air and earth, which is meteorology. For some time, in collaboration with Sinon Sukharyansky from Israel, we have been developing an advanced turbulence theory known as the quasi-normal scale elimination, or briefly QNSE. It's a theory of turbulence where we are dealing with highly fluctuating flow fields. And what we do, we ensemble average small scales, and we eliminate them from the equation of motion and develop equations for viscosity and diffusivity. What is good about this theory? First of all, it's almost analytical theory of turbulence, which is a unique thing by itself. There are very few theories which can go to the really first principles. But the theory can deal not only with neutral flows, which is kind of an achievement by itself, but also with stably stratified turbulence, which is anisotropic turbulence with waves. And rotating turbulence is in development now. So what this model can do is to produce anisotropic, scale-dependent, vertical and horizontal eddy viscosities and eddy diffusivities, which can be used in numerical models. also, because we account for the effect of waves, in this case of internal waves, we can produce dispersion relation for internal waves in presence of turbulence, something which didn't even exist until we developed it. Another advantage of the model is that it's free of the critical Richardson number, which is notoriously known to modelers because it's limiting, it has a tendency to limit and under-predicted turbulent mixing in the vertical. So I can show you what it produces. We can develop some results for weak stratification and for strong stratification. So this is weak, this is strong, arbitrary actually. So for weak stratification, well, this is nu is viscosity, it's vertical viscosity and horizontal viscosity, and kappa is diffusivity, it's horizontal diffusivity and vertical diffusivity. And nu n is a normalizing parameter, it's equivalent eddy diffusivity for neutral stratification. So I will not go into it, it's just for convenience because we want to operate with non-dimensional parameters. Ko is known as a Osmidov wave number. It's a wave number which it's a scale at which turbulence and waves have the same magnitude, and if we go to larger scales, K is a wave number, so it's inverse to the length scale. So if K is large, then the scale is small, and vice versa. If K is small, then if wave number is small, then the scale is large. So when we go to small scales and large Ks, the effects of stratification become smaller and smaller, and we collapse, we kind of come back to neutral stratification. So you can see that both viscosity and diffusivity become equal and equal to neutral stratification value, and I mean horizontal and vertical viscosity and horizontal and vertical diffusivity, they become the same as the neutral case. But when stratification increases, when we go to larger and larger scales, then the vertical viscosity decreases, vertical diffusivity also decreases, but horizontal viscosity and horizontal diffusivity, they increase. So you can increase stratification, but it doesn't mean that you suppress the forcing. You actually enhance the forcing in the horizontal, which is a very interesting result. But here we have a problem because viscosity and diffusivity both become zero, so we cannot use a model. But this is only approximation of weak stratification. When we go to arbitrary stratification, and we see that they don't go to zero, but viscosity, vertical viscosity remains, it's small, but it remains constant because of the mixing by internal waves. But with diffusivity becomes really small, and it actually goes into what we know today as the Osborne-Cox model. So the ratio between them is a turbulent Prandtl number, the ratio of viscosity to diffusivity, and the Prandtl number increases because viscosity kind of remains constant, but diffusivity decreases, so the ratio is increasing. So it's a very interesting thing because a lot of models which are used today assumes that vertical Prandtl number is constant and equal to 1, and when you go to strong stratification, this is just not correct. Dispersion relation for internal waves in the presence of turbulence is shown here. This is an analytical expression. Omega 0 is what we know from linear theory, but now turbulence adds all this nasty expression, which has a minus here. So when you increase K, at some point it will go to 0. So on large scales, you lose dispersion relation. If you consider turbulence and waves and look for difference between them, you can say that turbulence differs from waves because it doesn't have dispersion relation. So at some wave number, we lose dispersion relation. It means that we only have turbulence and no waves. And this is the picture of this nasty thing. It's omega divided by omega 0, and this is K over K Osmidov. So the wave can exist only inside this shape. Outside, it's only turbulence, no waves. We use this theory to calculate Dicker number. This is a very sensitive parameter of stably stratified flows because it operates with the second derivative of velocity profile and temperature, its potential temperature profile. And this is very difficult to measure. And because of this, it's not being taught in universities anymore. It's because it's very difficult to reproduce it. So we took QNSC results and compared them with data. This is what SMIT produces to plot this. You see for stratification, for temperature and for velocity, and this is data around it. So QNSC produces very plausible results. They decrease and then increase again. This Dicker number for velocity. For temperature, it decreases. If you look on other models which are empirical, they do all kind of unreasonable things. And if you use it in the model, you probably will have some problems. again, we can see the power of the theory because the second derivative of velocity is very sensitive to the way you parameterize other parameters. Now, HIRLAM is another application of the model. HIRLAM is a model, it's a numerical weather prediction system used in Scandinavia. It's high resolution limited area model. And we implemented our model there and calculated temperature in Sodankala station. It's a very cold area in Finland. And it had a tendency of under-predicting the 2-meter temperature. You can see that the problem was the model over-predicted it by about 20 degrees centigrade, which is huge. When QNSE model was introduced in it, you see the prediction drastically improved. Now, we can then put it in WRF, which is Weather Research and Forecast Model, which is developed in NCAR. But in WRF, we needed to use it for conditions of both stable and unstable stratification in convective boundary layer, also shallow stratocumulus. So the model was supplemented by a model which is known as mass flux model or eddy diffusivity mass flux model. So it was first introduced or worked with Julian Pergot, who put it in WRF with QNSE, but the model has not been tested yet and it's not fully developed. So this is one of the PhD tasks, one of the tasks of Samati, PhD. Now he is participating in EDMF comparison, model comparison with other models, and these experiments cover the testing of both QNSE and mass flux models. For example, he compared the QNSE and QNSE EDMF with large eddy simulation by Stevens, and you cannot see it very well. It's for temperature and water vapor ratio, but you see that when EDMF model is added, then agreement with LES improves for both temperature and water vapor ratio. Not always, but most of the time it does improve. So it makes a difference, particularly in the upper part of the boundary layer. Now we move to the second part of the talk, which is water and space. This research combines physical oceanography, planetary science, and also experimental physics. Studies basically will look into interaction between eddies, jets, and turbulence in various environments with different spatial scales. So first of all, let's look at jets and eddies on Jupiter. We know that the Reynolds number typical of Jovian circulation are very large. It's 10 to the 16. It's a really large Reynolds number. You cannot get to this in condition of Earth, even in the most advanced laboratories. So by our notions, people who took fluid dynamics, they know that this is well-developed turbulence. But the jets, so it will be very chaotic flow. But the jets and structure of Jupiter has been known for hundreds of years, and the jets don't change. You look at them any time of the day, any year, and you will see the same picture. This is a great red spot, by the way. So how is this possible? We have a clue to this. The flow is not laminar, but since it combines anisotropic turbulence and waves, it exhibits special features, which we call slow manifolds. And the time scale in slow manifolds is much slower than the rest of the flow field. So what happens is that jets form a slow manifold, and it has a very long time scale. So in fact, it's a very slowly changing turbulent flow. Okay, but this is a hypothesis which we need to validate, we need to prove it. Also, now we look at the eddies and jets in the ocean. This is 3 pictures taken from the paper by Shelton. It's a maps of sea surface height, taking one from Topics Poseidon, the other one is from Aviso, and the third one is a combination of the two. What is important here, it's very small, kind of small-scale features, but what is important is that the automated procedure applied to this picture identified over 3,000 different eddies in the bottom, in this panel. And 2,400 of them are traceable for 4 weeks or longer. So the ocean is full of eddies. If you average the eddies, it's another paper by Melnichenko and company, then you will see a collection of zonal jets going back and forth in the ocean, almost everywhere in the ocean. If you look on Jupiter, you will see similar thing. We already know about the jets, but of course the jets are much larger and much stronger than in the ocean. But they are also interspaced with different eddies. So this is a picture of eddies on Jupiter, and you can see that almost every jet has some eddies, large eddies associated with it. This is a great red spot. It's a special eddy which has been around for many years. But the eddies seem to be sitting in the areas of maximum shear. This is a maximum shear, you have another eddy. So every location of maximum shear has a big eddy associated with it. So this is a property of solitary waves. They're being fed by, well, they're interacting with the flow field, and they normally reside in places of maximum shear. This kind of study has not been done for oceanic eddies yet, so we don't know if this is the same in the ocean or not. But this is something which we can look at later on. Now, since both Ocean and Jupiter reveal jets and eddies, we traced the connection between the two and published a paper in JRL in 2004 and explored the connection using some turbulence modeling. Now, let's look a little bit into the physics of it. We can say that Jovian circulation is, because it's subject to strong rotation, it undergoes two-dimensionalization according to Taylor-Proudman theorem. And then we can apply quasi-geostrophic dynamics, and because there is a small-scale forcing due to convective plumes coming to the surface from the depths of Jupiter, we shall have inverse energy cascade from the small scale, which is about 100 to 100 kilometers, to larger scales. The size of the jets is in tens of thousands of kilometers. So there is a big range for inverse cascade. We understand the theory of two-dimensional turbulence. Classical theory tells us that if you have a, jumped a little too fast. If you have a forcing scale k psi, then on larger scales you will have inverse cascade with Kolmogorov-Kraichnan spectrum k to the minus 5/3, and to the smaller scales you will develop direct anstrophic cascade. But this classical theory is fully isotropic and it doesn't know anything about the beta effect. On Jupiter, however, we do have beta effect. So what happens on large scales where beta effect is important? We did some simulations, and there is a lot of work put into this. But what we found is that beta effect causes the turbulence, the quasi-geostrophic turbulence, to become zonostrophic turbulence. This is a term which we introduced into this science. It comes from Greek words zoni is a band or belt, and strophy is turning. So what is specific for all this corrupted, unfortunately, with this is that the zonal spectrum becomes very steep. You see, goes like n to minus 5, n is a wave number. But the non-zonal spectrum remains Kolmogorov and goes by the same load n to the minus 5/3. Those are the laws given in spherical coordinates. Now, when you go to large scales, the energy in zonal mode by itself is much larger than energy in all non-zonal modes combined. It's a very strong anisotropic regime. This mode by itself reveals the slow manifold features. So its time scale is very, very large, very long. And this is where the zonal flows reside. So if we can take zonal flows, compute the spectrum, and compare it with this curve, we can see if Jupiter regime is really zonostrophic turbulence. So this is what we did in 2001. We took the zonal profiles with zonal velocity from Jupiter and Saturn and computed the spectra, and you can see that this is a theoretical curve. And in both cases, they are pretty close to the data. Of course, it's a highly turbulent flow field, and it fluctuates like crazy. So in order to get rid of this noise, we need many realizations, which we don't have. We need hundreds of years of observations. So what is important here is a not only the slope, but also the amplitude. And the first time we did it, we got this agreement. We didn't try to fudge our results to the measurement. This is what we got from the model. Later on, there was some calculation by the Spanish group, Sanchez Levega and Barada Izaguirre, and they confirmed the same spectrum for the zonal flows. But can we say that Jupiter really reveals the anastrophic turbulence regime? We still don't have enough data yet, because zonal velocity profiles are only part of the picture. We also need to know what the non-zonal velocity will do. If we need to see if it can develop, if it exhibits Kolmogorov-Craignon spectrum. So from this data, we can compute rate of the inverse cascade and the anastrophy index. I just don't have time to go into it. Only after these two parameters also, this parameter conforms to the regime of the anastrophic turbulence, which is a threshold of about 2.5. Only after that we can really say that this is the anastrophic turbulence regime. So until very recently we couldn't do it because the data didn't exist. However, in December of 2000, Cassini had a flyby near Jupiter, and it collected the data for about 80 days, and for 3 days from this data are available for further analysis, and they have pretty good resolution. It was a big effort which we did in collaboration with Oxford University, and we just have a paper which is in press, not almost accepted in ICAROS, but it should be accepted, I hope, maybe even today. And then we could see that it's really the anastrophic turbulence. I will show you the proof a little later, but I just want to say that using the data we could also address other problems. First of all is the flow energetics, because we could now compute the energy transfer to zonal flows from non-zonal structures and also to the great red spot, and energy exchange between the zonal flows and the GRS. We could explain the large apparent energy conversion rate, which means that it was thought that too much energy, thermal energy, is transferred to zonal flows. We explained that this is not correct, that it's just it needs to be calculated in a different way. It was a very interesting question why the strength of circulation on giant planet increases with increasing distance from the sun, because we go far away from the sun, the energy is becoming smaller and smaller, but the circulation becoming larger and larger. So we also have explanation to this, and we also were able to compute meridional diffusive coefficient and explain some diffusion results related to the collision of cometary impacts into Jupiter. This is where the data was available. So first of all, let me show you zonal and residual spectra from Cassini. We have data which we processed with 4 different resolutions from 1 degree to 0.3 degrees. This is zonal spectrum, which is average over 5 points. You see that it sits very nicely over the n2-5 spectrum. So this spectrum is very difficult to now to deny. This is what we have. This is raw data, this is smooth data. But non-zonal spectrum now, the residual spectrum also looks very nice. You have a whole range here which exhibit n2-5 spectrum. Now what we do in turbulence, we plot not the spectrum by itself, but what we call a compensated spectrum, which means that if we know that it goes like n2-5 third, we multiply the thing by n2 plus 5 third, and the result then needs to look like a straight line. And indeed, you see that there are 2 different resolutions, and we have, well, here we have a very well-defined straight line. It's a Kolmogorov-Craignon regime. Here it's, the range is not very large, but it also seems to be a Kolmogorov-Craignon regime. So we have some discrepancy between them, but both indicate that the regime is there. So we can calculate now the rate of the energy cascade. So here's the estimation of the main parameters. Again, we see that this is zonal spectrum, this is non-zonal spectrum. We have intersection between them. This is wave numbers n beta and nz. The energy in zonal mode in Jupiter is much bigger than in non-zonal mode. It's 2 orders of magnitude. And we computed the epsilon, which was the first time ever, the rate of the inverse cascade. And the anastrophy index, which you remember should have been bigger than 2.5 to have the anastrophic regime, for Jupiter is way over 5. And such a big Oceanography index is absolutely impossible to obtain in any experiment on Earth. So if you want to reproduce Jupiter circulation, you need to go to Jupiter. Now, here's the zonal flow on 4 different planets. As I told you, you can see that the velocity increases even though the distance to the Sun also increases. Neptune has the biggest circulation of all the planets, but it's farthest away from all of them. The velocity here between maximum to minimum is about 800 meters per second. How can you explain it with such a small forcing? Well, the secret here is that velocity depends, if you remember, the spectrum depends on beta and number of jets, strictly speaking. Roughly speaking, it's a frictional wave number. It doesn't depend on the forcing. It's a specifics of this slow manifold that it depends on a very small number of parameters. So the most important parameter is beta, and it doesn't depend on epsilon. So even if epsilon is very small, if you wait for a long time, it will develop the slow manifold of magnitude, which we observe here. And of course, the age of this giant planet is billions of years, so they did have enough. They had enough time to develop the circulation. And you can see that the zonal spectra. Well, for Uranus you can question because we don't have much data. For Neptune we have 3 points, and they also sit on theoretical line, which is very nice. Now, experiment. This is what Jesse was doing. We have a collaboration with a group in Rome, at the University of Rome, and they have a facility with a rotating tank. And this is a unique facility. It's not large. It's under 1 meter in diameter, but they produce small-scale forcing by putting electric current through this and small magnets on the bottom. So they produce Lorentz force, which introduces vorticity or impulse in small-scale vorticity or small-scale impulse into the system. And when you combine it with rotation, then you will develop zonal jets. So it's very convenient apparatus because you can very quickly produce a large number of experiments. You cannot go to large values of R beta, but they seem to be comparable with what we see in the ocean. So we could study some of the effects of interaction between eddies and jets and turbulence. So JC went there and spent with people in Rome a couple of weeks. I think it was 3 or 4 weeks, and there was a big number of experiments. So this experiment particularly explains this is a beta plume. Okay, so we have series of magnets here, and they produce add momentum into this direction. The rotation is this way, and the beta effect is due to the parabolic surface of the fluid. So you can see that there is a jet in between, and there is a rotating eddies going with the system. All the system is moving with the speed of the most energetic Rossby wave, which is more or less what happens in the ocean. So if you look on this, you don't see a collection of jets. You see eddies and you see jets. If you calculate the barotropic stability criteria, Rayleigh-Coe criteria, you see that the system is intrinsically unstable. All 3 pictures are unstable, yet the picture does preserve itself as one union. And we didn't check the stability using the second Arnold criterion, stability criterion, but it's possible that the system is barotropically unstable, but stable by Arnold too. So this is something which JC needs to look at. However, interesting thing is that when you average everything in time, you don't see any eddies anymore. You see alternating zonal jets, exactly what we see in the ocean. So this thing may actually help us to understand oceanic jets and eddies and how we distinguish between them. There is some diffusion properties, for example, which are related to turbulence, and they're specific to turbulence. We can measure them here, and we can measure them in the ocean, and this is a very interesting thing if we arrange for the comparison. There is some technique which is going to be used here. It's a final scale Lyapunov exponentials, which is developed for this technique, but I think it's just being in studies in stages of development for the ocean. So another thing is that when you look on the spectra, you also see an interpretation. There is more energy in zonal spectrum than in non-zonal spectrum, and the slope begins to approach the anastrophic regime, which is, well, the ranges are very limited, so we cannot really seriously talk about it, but we can still evaluate numerical values, and they may be useful for future analysis. So now I can just go into conclusions. We know that anisotropic turbulence and waves underline many important atmospheric, oceanic, and planetary phenomena. QNSE theory is a good theory which may help to develop better numerical weather prediction models. This is what I'm really proud of, this, that we developed a new universal turbulence regime, which is anastrophic macro turbulence, and we found it really to exist on giant planets. It also may be important for extrasolar planets, because Jupiter's seem to be quite common in planetary systems. Now we can use laboratory framework for studies of jet and turbulence and interaction between jets and eddies. And well, I can tell you that now we come back to the first slide, that studies of geophysical fluid dynamics apparently stimulate mind and spirit and improve harmony with the environment, again, as long as it doesn't have red tide.